Hello dear students. So in the last class we have defined three types of boundary value problems: Dirichlet boundary value problem, Newman boundary value problem and Robin problem. Now the question is, we are not sure whether each of these problems will possess a solution. If the solution exists, that is unknown. And many mathematicians have proved that if the domain D is sufficiently smooth, then the Dirichlet problem always has a solution. Okay. Now sometimes what happens is, when the given domain D will be a rectangle or some domain where there are sharp edges, so we can see that at those points the given function, the solution will not be differentiable. So we will not get a smooth solution. So it is difficult to find a solution as such in that cases. In as far as the context of this textbook, we will limit ourselves to classical solutions, that is solutions that have twice differentiable, and the solutions that belong to C to D. Okay, two times differentiable functions defined in a domain D. So we will mainly concentrate on that those solutions, how to find them. Okay. So now coming to a Newman problem. We have lemma 7.4, which gives the necessary condition for the existence of a solution to the Newman problem. So I hope you remember what is the Newman problem. So the problem, Newman problem is actually, it is the function should satisfy delta u equal to f of xy inside the domain D, and on the boundary we have a derivative condition, that is the derivative of u in the direction of the outward unit normal should be the function g of xy where xy element of boundary of D. So this is the Newman problem. So the condition says that this will have a solution. The solution will exist if integral over d, g is the value of the derivative on the boundary, that is equal to integral over d f of xy dx. So f is this value, so it means that when you integrate f inside the domain D, okay, so if this is the domain D, when you integrate f inside the domain D, that should be equal to the integral of g, which is defined on the boundary, and if you integrate g over this boundary. So if these two integrals are equal, we say that we can say that the Newman problem has a solution. Okay, so we will see the proof. So I hope this delta u, you are familiar with this delta u. What is this delta u? This is nothing but actually this is Laplace equation. So it is the second derivative, dou square u by dou x square plus dou square u by dou y square is delta u. Okay, this we can write this as del dot del del u. Del is a gradient operator. We know del dot del is nothing but del square u. Okay, so del square is written like delta. Okay, so this is nothing but del dot del. Okay, so it means that we can write our problem in this way. We'll write it here. So instead of delta u, I can write this as del dot del u. They are gradient operator. Del u is equal to f of xy. Now suppose that I integrate both sides over D. Okay. Integrate both sides over the domain D. So I will get integral over D. Here RHS is f of xy. So we have two independent variables x and y. So here I have dx dy is equal to, again, integral over D. Here I have del dot del u, here I will denote it by dv. Okay, now we can see that this is of the form del dot f. Okay, you must remember the Gauss divergence theorem. Okay, so by the Gauss divergence theorem we have triple integral over v del dot f dv. Okay, del dot f dv. So here we have triple integral over v del dot f dv is double integral over s f dot n ds, f dot n ds. So this is the Gauss divergence theorem. We will apply it here. So del u is our f. Okay, del dot f. So this is our f. So we will get that this is equal to f dot n ds. Okay. So what we will get here is double integral over d del dot del u dv is equal to, this is S is the surface. Okay, so we can represent it by boundary of D. F dot n. So F is del U. Okay, del U dot n ds. So here we are doing a reparameterization, that is we will take in the boundary, we will take the using the arc length S as the parameter, we are reparameterizing it. Okay, so x of s, y of s is a parameterization of boundary of D. Okay, so this is a parameterization of boundary of D. So what we are getting is, now del u dot n. This is del u dot n is nothing but by the Poisson's formula. This is same as dou u by dou n. Okay, del u dot n. Hope you remember that dou by dou n is nothing but n cap dot del. Okay, so dot product is commutative. So del u dot n is nothing but dou u by dou n. So I can write this as integral over the boundary D. Del u dot n is dou u by dou n, and here we have the parameterization. So here I have x of s, y of s, ds. Okay. So now we will substitute the value here in this equation. We will substitute here. So we will get integral over d f of xy dx dy is equal to integral over the boundary. So this is actually the double integral. Okay. Now what is dou u by dou n? The problem we have defined that our problem is del u equal to f in D, and dou u by dou n is equal to g in the boundary. Okay, so this is our problem. So in the boundary dou u by dou n is g. So we have g of x of s, y of s, ds. So this is the necessary condition for a Newman problem to have a solution. Okay. Now from here we can also say that if you take for any harmonic function, so from this theorem or the result we can say that for any harmonic function we can say integral over gamma dou u by dou n ds is equal to 0 for any closed curve gamma that is fully contained in D. If that gamma is fully contained in D, this we can say, because we know that this is true for any harmonic function, because we know that harmonic functions are, if I say harmonic function, this is true for any harmonic function, because when I say harmonic function, it means that it is a solution of Laplace equation. So solution of Laplace equation. So in Laplace equation, this f term is not there. Okay, so it is delta u equal to 0. F is 0 here. So if you apply in this theorem, if you apply here, you will get f equal to 0. So RHS is 0. So you will get in this theorem g. G is nothing but dou u, the boundary, the dou u by dou n, the derivative with respect to the normal. So we can say that integral over any region gamma which is fully contained in D, dou u by dou n ds is equal to 0, because dou u by dou n happens to be the integral of this, but f is 0 since it is the Laplace equation. Harmonic functions are solutions of Laplace equation, and Laplace equation is delta u equal to 0, so here f equal to 0. So when you put in the above theorem f equal to 0, so we can say that if gamma is any curve which is fully contained in D, integral over gamma dou u by dou n ds is equal to 0. Now we can all we will give some small definitions. That is, we define a harmonic polynomial of degree n. We define a harmonic polynomial of degree n to be a harmonic function. P on a harmonic polynomial is nothing but a harmonic function Pn of xy, which is of this form. That is, Pn of xy is equal to summation a I comma j x raised to I y raised to j, and we have the variation 0 less than or equal to I plus j less than or equal to n. So this is the definition of, so harmonic polynomial of degree n is a harmonic function So it's a harmonic function Pn of xy, which is of this form. Okay. So for example, if I write x minus y, you can see that the degree is 1. So it is a harmonic polynomial of degree 1. Okay. So this is a harmonic polynomial of degree 1. Similarly, if I write x square minus y square plus 2x, again it can be written in this form. So it is a harmonic polynomial of degree 2. Degree 2. Similarly, we can write x cube minus 3xy square minus y. So it is of degree 3. Okay. Now we consider another subclass Vn of, suppose we denote the harmonic polynomial, and we consider its subclass, which is of the form, so it is a subfamily of the above class. So we consider summation aij x raised to I y raised to j, where I plus j is equal to n. Then this is called the set of homogeneous harmonic polynomial. So it is they are the homogeneous because the degree will be same. Homogeneous harmonic polynomial. So here you can see the first one. One second. Here you can see in x minus y it is homogeneous, but in here this is not homogeneous, this is not homogeneous. So this homogeneous harmonic polynomial form a subclass of this. Now we will also consider in some cases, in some problems, they are all just definitions, we will use it somewhere. So we will also consider Laplace equation in polar coordinates. So Laplace equation in polar coordinates is also important. Laplace equation in polar coordinates. So we will usually take r theta to be the variables and the function w of r theta to be, it's a function of u is a function of x and y. Now x is a function of r and theta. So x of r comma theta, y of r comma theta. Okay. Then the Laplace equation in polar coordinate. Laplace equation in polar coordinate is this: delta w is equal to 0 and it is given by wrr plus 1 by r wr plus 1 by r square w theta theta equal to 0. So this is easy to derive it. Okay. So in Laplace equation in Cartesian coordinate we have it as uxx plus uyy equal to 0, but in polar coordinate it takes this form: wrr plus 1 by r wr plus 1 by r square w theta theta equal to 0. So this is the Laplace equation in polar coordinates. Okay, so we will stop here. Thank you.